生文可带生命的。作业一点太多，做还写错。这个钱，这一点的钱。没有，我直接听不懂。听不懂就。第一题的话，第一题我觉得不是第一题完全技术的小。我记得你没有对到那个做。我一块是什么？一块是别的。
Okay, so let's continue. Okay. So. So we want to see some examples of the kernel range. Okay, so prove that LV equal to AB is a linear transformation from R3 to R2. If A is a 2 by 3 matrix, so and V is R3. Okay. So first, we want to see this is a linear transformation, right? So LV equal to AB. So the important thing is L alpha AU plus CB, okay, equal to A minus alpha A AU plus BB. This is going to be, A minus A AU plus B minus A B. So this is going to be A minus LU plus B minus LU. So this one is so we know that this is as long as A is a matrix, okay, A is a matrix, and this AU plus PV can be we have like distributed one, and then we can get the A out, the B out to the front, and so this will be the consequence, okay. Then we want so once we know like this LV equal to AV is a linear transformation. Then we can talk about the kernel and range, right? So for this particular A, okay. So what is kernel? Kernel means A, B equal to 0, or the B, right? Or the solution for B, right? So it's going to be 1, negative 2, 2, 5, 3, 4. So you have like so you use get like you know the solution for this one. This is what? This is basically the null space of this matrix, right? This is the null space of this matrix. Okay, so I will stop here because like the null space we have discussed like many times, like in the previous structure. So you know like how to calculate null space. Okay. And how about range? Range means what? Range means the AB equal to A equal to W. Okay, then you know there exists a B such a match to W. So all the W. Okay, so it's basically like you can treat it as a linear combination of it's going to be like the space spanned by the column space, column vectors, right? No, if there's a linear combination for this one, I mean, we can get such a you know vector, and we know like there exists like you know like an x y z, okay, that form that vector. Okay. So basically, kernel is basically the null space of this of A, and the range is basically the space spanned by the column vectors of your you know matrix A. Okay. So from there, okay. Prove that if A is an n times n matrix, then LV equal to AB is a linear transformation from Rn to Rn. And the dimension, kernel, cross dimension, range, A equal to n. Okay. So, first, as I said, like, what's the term for that? In the previous chapter, we talked about theorem similar to this one. you remember, no space discussion. And we talk about dimension. We talk about that's pretty much like our color space. I mean, this one is the space that is expanded by the color, right? The range of L is basically the same as the color space of A. Okay, and the dimension of row or column space of A is called the rank of A. Okay. And we have proved here the rank of A, okay, which is the column, the dimension of column space. Okay, plus the nullity, which is the nullity of A, which is like the kernel. Okay, the kernel, as I said, is the kernel of L. Basically, is like the null space of A, right? So these two, the dimension of these two, add up. So we have proved this previously. Okay? Now I'm just trying to connect the new concept with the old one. Okay? I mean, if like linear transformation does not have to be a matrix. It's just like if linear transformation is defined over a matrix, then the new material has some connection with this one. Okay. So we have like this big. Okay. So how do we find the kernel? Yeah, this is like exactly what I basically just solve this equation, and it will give you this one, which means like it is like one dimension, and then this range is the span of this, which is we can show that this is a two dimension. So 1 plus 2 is 3. Okay. It's n by n by 3 by 2 by 3. So 3 equal to 1 plus 2. 1 plus 2. So we have finally finished like the first section. For the second section, I do not think we can finish this section today. Okay, but we will talk a little bit about this. But I think I will not cover this part in the midterm. Okay, the midterm will cover up to the first section of chapter 4. Okay, the first section, not the second section. I mean, I will still cover the second section today, but yeah, I'm not going to finish it anyway. Okay, so. Assume V and W are respectively n and n dimension vector space. B1 equal to this, and B2 equal to that are the bases of V and W of W. If L B to W is a linear transformation, then you can sort of like represent your linear transformation. Okay, L B B2 equal to A B B1. Okay, so it's with AJ equal to L BJ B2. So what exactly are we talking about? Let me use an example. Before I give a proof, let me use an example. L xy equal to 2x plus 3y, 4x minus 5y. So if I use like this is obvious like from two dimension map to like it could be two dimension too. But anyway, so let's consider LE1. Okay, E1, E2 are will obviously be the standard basis for B, right? So you copy this one, you get this. This one can be written as 2E1 plus 4E2, right? LE2 equal to this one, which will be this one equal to 3E1 minus 5E2. So you can write your linear transformation. Okay, originally it's like that, but now you can represent it as a vector, as a matrix times a vector. Okay, this is respect to the standard basis E1, E2. Okay, this is with respect to the standard basis. But I mean, we know that a vector space does not have to use like a standard basis, right? We could use like any basis to represent a vector space, right? And one thing I want to show you is like this. This is 2, 4, right? So 2, 4 here as a column vector. 3, -5 here as a second column vector. Okay. Because we use standard basis, nothing to be written in addition to showing the visuals. Okay. But if we have a little bit more complicated thing. Okay. A2 x squared plus A1 x plus A0. Okay. A2 it is mapped to 2a2x plus a1. So this is obviously a differential operation from P2 to P1, right? This is differential operation. I mean, you know how to do a differentiation, right? Okay. So then, for the first P2 is three-dimensional. You have A2, A1, A0. So the easiest approach is just like we said, like the first like the basis for the first P2 is 1 0 0 0 1 0 0 0 1. Okay, so 1 0 0. If you put this one out into like a differential operation, what you get is like a 2x. The 2x is like if you consider like the second base is like x and 1, then it's going to be 2 0, 2x and 0 0 1, right? And 0 1 0 basically means one single x. So after differentiation, you get a 1, okay, which is 0 1. And 0 0 1 after differentiate, we get 0, so 0 0. So if you want to represent this differential operation, we know that differential operation is a linear transformation. We proved that in previous. But now we are in a position to represent this linear transformation into a matrix for O1, which is like this. But this one is like from P2 to P1. From P1 to P2, okay, from P1 to P2. This differentiation is from the first basis, P1, to the second basis, P2. So it is represented like that. Okay? So bases are different. Well, actually, we are talking about two different vector spaces, right? First one is P2, second one is P1. So they obviously have like a different basis. And how about this one? Okay, Lxy equal to 2x minus 2y, 3x plus 4y, negative 7x. Then similarly, we apply E1, E2, E3, so E1, E2, because it's two-dimensional. Probably so E1, we get 2E1 plus 3E2 minus 7E3. Okay, because the B is two-dimensional, W is three-dimensional. So its basis are different, even though we are both standard basis. So E2, okay, we probably get like this one is negative 2E1 plus 4E2 plus 0E3. So you see 2, 3, negative 7 to here, negative 2, 4, 0. And it's xy. Okay, so this represents how we map from like standard basis of two-dimensional into standard basis of three-dimensional. Okay, this is linear transformation. So, one more thing, okay. As I said, like we could be using like a different basis, right? So here, okay, it's we are talking about the same linear transformation. We're talking about same linear transformation, but for the two-dimensional part, okay, for the D vector space D, we use E1, E2. For the W, we use like the B2, which is a little bit complicated, like, but it is a basis. You can verify this basis by yourself. I will not get into a detail, but you can verify that easily. It is a basis. So these two things, Okay, you plug in the E1, you get 2, 3, -7, which is actually the same, 2, 3, -7. But originally, we try to represent this as like the standard basis for the 3-dimension. But now we do represent this one as like a linear combination of this basis. So it's -5, this one, -2, this one, plus 7, this one. So it's going -5, -2, and 7, B2. Okay? And similarly, okay, we plug in 0, 1. This is how we got. But we need to represent this one as a linear combination of the B2. Okay? And then we get -2, 2, 0, -2, 2, 0, B2. So, having said that, you can put -5, -2, 7 here, and the -2, 2, 0 here, and this is like from P1, which is the standard basis. And if you apply, this linear transformation, okay, if you want to represent the result of this linear transformation into the basis 2, then your linear the B1, the basis using the B1, modify this one, you get that the result of like the coordinate, okay, of like what you get for B2. So you can see that the same linear transformation. This is the same linear transformation. The previous one, this one, and this one. Okay, but when you consider different bases, okay, you are going to represent this linear transformation differently. But of course, you have to specify. This is for that B2, and this one is from B1, B1 down to B2. Okay, this is the matrix for that. I mean, if you want, we can also represent this one as like the first basis, first standard basis, and map to the from first standard basis into the second standard basis. But because it's standard basis, so we don't need to write it like a specific. Okay. Because everybody uses the standard basis all the time. Okay. So having said that, okay, let's go back to this one. Assume V and W are respectively n and n dimensions, vector space, and B1 is like that, B2 is like that, are respectively basis of B1, V and W. And if L, B to W is a linear transformation, then L, B, B2 equal to A, B, B1. Okay, where AG is actually a column vector. Okay, so you represent like each vector B1, B2, B2, B3, etc. Each vector by the basis of like B2. Okay, after the linear transformation, of course. So you plug in B1 into the linear transformation, and then you represent that as B2 to get the coordinate. That coordinate is your column vector. You do that for every like a basis vectors in B1, and that's how you get your matrix A. A is called the matrix representation of L with respect to the order basis B1 and B2.